So there are other ways, of course, to improve an infinite series, convergence or divergence. And another way to do that is to take a series that you already know about and use that as a comparison to a new infinite series. So you pick one that you already know about or that's easy to prove the convergence or divergence with a different way. And then there's two different ways to compare it to an unknown series. And you can use that comparison to say whether or not the new series is going to converge or diverge. So the first way to do that is by something called the direct comparison test. So two things have to be true in order to use this. Your sequences A of n and B of n have to be positive. They have to be greater than or equal to 0, right? And remember, A of n and B of n are just the sequence rules that are inside the infinite series. So there's two things that can happen. If you know that the sum of B of n converges and B of n is bigger than A of n, right? B of n is the bigger one, right? So this is the bigger sequence. If the bigger series converges, the bigger sequence converges, then the smaller series also has to converge, right? And that makes sense. If something that's bigger converges, anything that's smaller than it that's similar is also going to converge. And then we have the opposite. If you take the smaller sequence, A of n, and that one diverges, like you know for a fact that that one diverges, then you can say, well, if the smaller one diverges, the bigger one also has to diverge. So something that's really tricky about this one is you have to state the inequality. You have to say which one is the smaller one and which one is the bigger one in order to use this. So I personally, between the two comparison methods that we're going to talk about, I like the other one better, but this one works really well for some basic things too. So we're going to go over how to do these. So we're going to look at a few different examples quickly. So we're going to determine if the following series converges or diverges, and of course, we're going to use direct comparison. So again, we just always want to quick take that nth term test, right? So if we take the limit as n goes to infinity of 1 over n cubed plus 1, that's going to 0, so we can't say it diverges by nth term test. So we can go ahead and move on from there, right? So it fails the nth term test. So then you want to say, okay, I have 1 over n cubed plus 1. If we're using a comparison test, you want to pick a simple series that is very similar to that one. So 1 over n cubed plus 1 is very similar to the series from 1 to infinity of just 1 over n cubed, right? 1 over n cubed, very similar to 1 over n cubed plus 1. So you want to use those very similar series, right? And we know, because this is a p series, right? And the exponent is bigger than 1, right? 3 is bigger than 1, right? We can say this converges by the p series test. Right, p is greater than 1. Right, so you want to pick a series that you can very quickly prove the convergence or divergence of. Now, since this converges, we want it to be bigger than the one that we're trying to prove about. Right, so for convergence in direct comparison, convergence, right, we need 0 to be less than or equal to a of n, less than or equal to b of n. Right, where we know this one. Right, we know this converges. So we need to make sure that converges. I don't know why I can't spell today. So we need to make sure that this convergent series, 1 over n cubed, that we already know about, we want to make sure that that's bigger than the one that we're trying to prove. So what we're going to do is we're going to set this up. We want to say, okay, is 1 over n cubed plus 1 always less than or equal to 1 over n cubed? All right, question mark. Right, so if we cross multiply here, we get n cubed is less than or equal to n cubed plus 1. Right, and if we subtract n cubed from both sides, we get 0 is always less than or equal to 1. Right, that is a true statement. So we can say, right, 1 over n cubed plus 1 is always less than or equal to 1 over n cubed. Right, so because we can show that inequality, right, and this is for all n greater than or equal to 1 because that's the domain, right? That's where our starting value is. So we can say because of this, right, therefore, right, right? The sum from 1 to infinity of 1 over n cubed plus 1 converges by direct comparison to the infinite sum from 1 to infinity of 1 over n cubed. Right. So the direct comparison test works really well for things that are similar to p-series, but are not an actual p-series because there's extra parts. So example B is another great type of function to look at, type of series to look at, because we have 1 over 3 to the n plus 2. So if we quick do our nth term test, just to make sure we can't just like stop here and then move on to a new problem, right? If we take the limit as n goes to infinity, we know that's 0, fails the nth term test, got to do something else. So, right, if I just were to get rid of the plus 2, right, then we have a very nice simple series that's actually geometric. 1 over 3 to the n is geometric. So let's compare this, if my pen will not be white anymore. All right, let's compare this to the sum from 1 to infinity of 1 over 3 to the n, which I can also write as, my summations are awful today, that's okay, right? 1/3 raised to the n, right? And this is geometric, right? We can see that common ratio being raised to a power, right? Right, which is convergent by the geometric series test, right? And I know it's convergent because geometric series test, because our ratio is 1/3, and 1/3 is less than 1, right? Since the absolute value of r, which equals 1/3, is less than 1. Right, just quick and simple, you have to just know straight off the bat, convergent or divergent. So you want to use these very simple series. So again, this is convergent, so we want it to be bigger than the series that we're trying to figure out. So we need to prove if is 1 over 3 to the n plus 2 always less than or equal to 1 over 3 to the n, which is what we know about. Right, again, we cross multiply, so 3 to the n less than or equal to 3 to the n plus 2. Right, 0 is always less than or equal to 2, that's true. Right, so we can say therefore, put this down here, right, therefore, right, 1 over 3 to the n plus 2 is always less than or equal to 1 over 3 to the n, right, for all n greater than or equal to 1, because that's our domain. Right, so we have to state that that inequality is true. So because the bigger sequence we know is convergent, the smaller sequence is also convergent, right? So therefore, this infinite sum, 1 over 3 to the n plus 2, converges by direct comparison to the sum from 1 to infinity of 1 over 3 to the n. Okay, so let's do one more example just because I feel like these can be a little tricky. So let's look at this, right? This looks a little different, right? We have cosine of n from 1 to infinity over 2 to the n. And actually, that should be n pi. That was a typo. Okay, so this is actually kind of a hidden oscillator, right? So, right, if we think about cosine of n pi, and n is an integer, so we have like 1 pi, 2 pi, 3 pi, 4 pi, like so on and so forth, right? The values of cosine for like 1 pi, 2 pi, 3 pi, 4 pi, right? That's just going like a half turn around the unit circle each time. So cosine is oscillates between -1 and 1. Right, so, right, technically we do the nth term test, right? So the limit of this thing, right, cosine of n pi, right, that's oscillating between -1 and 1. So we can also write this actually as the sum from 1 to infinity of -1 over 2 to the n, right? And then we want it to go 1 and then -1, 1 and then -1, so this is going to be n plus 1 there. Or you can also write it like that. You'd get the same values each time. So if we take the absolute value of that and then take the limit of that overall function, that thing's going to 0. So it means that the limit of the overall sequence is also going to 0 by that absolute value theorem for sequences. So nth term test fails here, so we have to use direct comparison. Let's just jump right into that. So, right, let's compare this to, right, the sum from 1 to infinity of just 1 over 2 to the n, right? And that's a convergent geometric series as well. Right, because our ratio is 1/2, 1/2 is less than 1, so we're all good. Right, so now we need to show whether or not cosine of n pi over 2n is always less than or equal to 1 over 2n. Right, so if we cross multiply, right, since they have the same denominators, in this case we can actually just like get rid of the two denominators. So is cosine of n pi always less than or equal to 1? Well, cosine is always going between -1 and +1, so it is always less than or equal to -1, right? This is a true statement, right? So we can say therefore, right, cosine of n pi is less than or equal to 1 over 2 to the n for n greater than or equal to 1, right? So then we can say that this infinite series from 1 to infinity of cosine of n pi over 2n converges by direct comparison to the sum of 1 to infinity of 1 over 2 to the n. So like I said earlier, this actually isn't my favorite way to do comparison. I actually really prefer something called the limit comparison test, which is what we're going to look at now. So you can also prove convergence or divergence of an infinite series by looking at two sequences and finding the limit of their ratio. So again, we're going to use two positive sequences. Remember, those are those sequence rules inside the infinite series. And we're going to divide them by each other. So it doesn't matter if you put the A or B in top. Right? If you take the limit of the ratio of the sequences as n goes to infinity, and that equals a limit value, like the limit exists, and L is finite and positive, right? So it has to be a positive limit value. Then the two series either both converge or both diverge. So again, this is going to be a scenario where you have a series that you don't know about. You're going to pick a similar series that you do know about, whether it converges or diverges. So again, a very simple series to look at and prove convergence about. And then if you can show that the limit of the ratio equals a number, right, then they either both converge or diverge. They do the same thing. So we're going to look at two quick examples of this. Right, well, let's determine if this thing converges or not. Right, so we'll quick first do our nth term test, right, the limit of n going to infinity of n to the 4th plus 10 over 4n to the 5th minus n cubed plus 7. Right, I have a higher degree in my denominator, so this is going to 0. Okay, so fails the nth term test, so we have to try something else. So let's compare it to the sum from 1 to infinity. Now, this one we just have to get a little creative. So if we look at this function, if we look at the beginning part, right, the highest power in the denominator compared to the numerator, right, if we were to just take that and simplify it, this kind of goes down to 1 over like 4n, right? So we can compare this to just 1 over n. So let's compare this to the harmonic series, right, which is the divergent harmonic series. Okay, so this is divergent, which means that if we take the ratio and the limit equals a number, the original series also divergent. So let's look at the limit as n goes to infinity, and I'm going to put my original one on top. So n to the 4th plus 10 over 4n to the 5th minus n cubed plus 7, right? All over the one I'm comparing it to. Right, so since I'm dividing by a fraction, right, I'm going to really multiply by the reciprocal. So that's going to be n times n to the 4th plus 10 over 4n to the 5th minus n cubed plus 7. Right, and hopefully you can see what's happening, but I'm going to write out the arithmetic in one more line. So if I distribute that n through, right, the limit of that, now that we have equal degrees in the numerator and denominator, right, just ratio of the coefficients, so that is 1/4, right, which is greater than 0, right? We get a positive limit value. So because we get a positive limit value and we know that the harmonic series is divergent, it means the original one is also divergent. So we can say, right, therefore, the sum from 1 to infinity, the series from 1 to infinity of n to the 4th plus 10 over 4n to the 5th minus n cubed plus 7 diverges by limit comparison to the harmonic series, which is 1 to infinity of 1 over n. Okay, so let's pick another one. Okay, so we have, right, the sum from 1 to infinity of 1 over the square root of 3n minus 2. Right, so first let's quick try our nth term test, right? I have no variables in the top. I'm sorry. This I typed in wrong. This should be a regular, and it looks like an exponent, but it is a regular n. Okay, so that is going to be, let's see, we have bada bing, bada boom, that's going to be 0, right, because all the variables are in the bottom. So let's compare this to the sum from 1 to, not I, nope, nah, that's not an eraser, to n equals 1 to infinity. So if we pick something super similar, right, you're really just taking out all of the extra stuff in the problem. So I'm going to take out that minus 2, and I'm going to take away the coefficient of 3, and then it's going to be pretty similar to 1 over the square root of n, right? And then I can rewrite that as 1 over n to the 1/2. So now it looks like a p-series. And so my exponent in the denominator is 1/2, which is less than 1, right? So this is a divergent p-series, right? Or you can say it diverges by the p-series test, right? We can say explicitly since p equals 1/2, which is less than 1. Okay, right, so again, another divergent example. So let's take the limit as n goes to infinity, and let's do the one we're trying to prove on top. So 1 over the square root of 3n minus 2, all over 1 over the square root of n. Right, so keep, change, flip if you like that little wordy notation. Hope you remember, right, multiply by the reciprocal. So it's going to end up being the square root of n over the square root of 3n minus 2. And that's really just equal to the limit as n goes to infinity. What am I doing there? That was not an infinity sign. The square root of n over 3n minus 2. So the limit of the inside is just going to be 1/3. So our overall limit is just the square root of 1/3. And the square root of 1/3, right, that's a positive number, so we're good here. So because we got a positive limit, we can say therefore the sum from 1 to infinity of 1 over the square root of 3n minus 2 diverges by limit comparison to the series from 1 to infinity of 1 over the square root of n. So I like limit comparison more just because I don't have to prove that inequality statement and I don't have to remember which way it goes in. And I actually really like rational functions and doing like fractions divided by fractions, so this was more my wheelhouse, but you can use whichever one you want as long as the problem doesn't specify what you have.